So a capacitor is a device which is used for storing charge, and the measurement of that is called its capacitance, and it's quite a simple definition which once again will link to the formula, you can use that. But capacitance is the charge stored per unit of voltage. So basically, in order to get charge stored onto a capacitor, you have to apply a voltage. And what we find when we do the experiment is that there's a direct proportion between the charge stored and the voltage. If you measure for different voltages, you get direct proportion, and we call that constant of proportion, the gradient of that line, then the capacitance. Now we'll do a quick worked example. So we're given that the charge is 4 times 10 to the minus 4 coulombs, and the voltage is 100 volts. And we've been asked the capacitance. C equals Q over V, 4 times 10 to the minus 4 over 100 equals 4 times 10 to the minus 6 farads. And we quite often find that micro, milli, nano, pico even are quite common units for the charges and the capacitance involved. The unit of capacitance is a farad. F. Now, to charge a capacitor requires energy, or work must be done to charge a capacitor, because when you store some charge on that capacitor, so when you move some charge from one plate, leaving it positive, and push it onto the other plate to make it negative, then the charge that's already there will then try and repel away any further charge. So because charge already stored on the capacitor will repel further charge. And basically then the more charge that you store in that capacitor, the harder it's going to get. Now we know from our work in electric fields that the work done in moving a charge through a voltage is given by QV. But if we do a quick reminder of the equation we met right at the start, then we can see that Q and V both change when you're looking at a capacitor. So the work done has to be averaged out. Okay, and the work done is the area under a QV graph. And if you took it there to that point, say it's fully charged, then you see you get a triangle, and that gives us the relationships then between energy and charge. So the energy stored in a capacitor is the same as the work done in charging it, because you can get that energy back. And because you're having to average out, it's given as a half QV. And because we know Q can be written as CV if you rearrange the capacitance equation, that can also be written as a half CV squared. And once again, substituting for V equals Q over C, you get a half Q squared over C. Do a quick worked example of that as well. So in this example, we're told the capacitance 40 microfarads. Remember, convert your prefixes when you're listing your variables. And the voltage is 50 volts. And the energy stored then we're going to use a half CV squared. Watch you don't mix up your capacitance and your charge. Okay, they're not quantities we use that often, so, and there's lots of C's flying about as well, so remember C stands for capacitance when you're looking at the symbols, but its unit is farad, and Q stands for charge in the equations, but the unit is C for coulombs. Okay, that can be easy to mix those up, but then just substituting in to this example. And we're not talking about big energies. Okay, once again the charges and stored usually are milli, micro, etc. So the energies aren't big as well. Now, one of the things you've got to watch with this equation is if you look at two different voltages, so say you were comparing the energy stored at 50 volts here with energy stored at 70, you can't take the difference in those two voltages and plug it into the equation. You've got to work out the energy at 50, work out the energy at 70 and take the difference. Okay, it's not direct proportion between energy and voltage. Right, it's proportional to voltage squared. Now up to now we've been concentrating on what happens when a capacitor is fully charged. And at that point the voltage across the capacitor equals the voltage across the voltage of the supply, and that's when you've pushed as much charge on as you can. In the next section though, we're looking at how you actually get to that stage. So looking at how it changes with time to reach that point of being fully charged. And we need to be familiar with the shape of the graphs, and then we'll look at the next one about what happens if you change some of the values. Okay, so first of all, when we're looking at charging, we'll display the graphs together for both charging and discharging. And I'll try and just display these as one big graph. So if we're looking at the voltage across a capacitor versus time, then it builds up and then flattens out at the supply voltage. And then if you then set it to discharge, you get the opposite sort of shape, flattening out at zero. And we know it's fully charged then when the voltage across the capacitor equals the supply voltage. That's when you can't get any more current moving around the circuit, so the push of the battery is cancelled out perfectly by the push coming back from the capacitor. You've pushed as much charge on as you possibly can. And we know it's fully discharged when the voltage across the capacitor goes back to zero. Now we don't get asked as much, but the voltage across the resistor is linked closely to the voltage across the capacitor. But it will have positive and negative values, as we'll see in a wee second. So basically it starts at supply voltage. At all points in time, the resistor voltage and the capacitor voltage add up to the supply voltage. So when the voltage across the capacitor is 0 to begin with, then the voltage across the resistor is Vs, but as that voltage across the capacitor builds up, the voltage across the resistor is going to decrease down to 0 and go along at 0. But then when you discharge, you take the battery out of the circuit and you've just got a closed loop with 0 voltage in it. You've not got any supply voltages in it. So the total voltage around that loop must be 0. So at that point the voltage across the capacitor is plus Vs, which means the voltage across the resistor at that instant must jump to minus Vs. And then as the voltage across the capacitor decreases down towards 0, so will the voltage across the resistor. Now that gives us the shape of the other graph, which you are asked a bit more often, which is about the current flowing in the circuit. And because voltage and current are proportional for a resistor, it will follow the exact same shape as that graph we've just looked at. but it will be plus Vs over R and minus Vs over R in these. So same shape, going down to 0, jumping negative when it discharges because the charge is now flowing off of the capacitor rather than onto the capacitor. So it's flowing in the opposite direction. Now for outcome 6, we'll concentrate on the charging curves, but the exact same logic can be applied to the discharging curves as well. And that's what happens if we change the value of capacitance or the value of resistance. So first of all, looking at capacitance, if you look at the voltage across the capacitor versus time, and previously we had that kind of building up towards the supply voltage. If we used a smaller capacitor, then that means it can store less charge, which means it will fill up quicker. You're using the same supply voltage. It will still reach the same value, but it will reach it quicker and then go along flat at those values. So smaller capacitance means a quicker charging time. Similar sort of effect if we have a smaller resistor in the circuit, then the current involved will be bigger, and so it will charge more quickly. So smaller capacitance or smaller resistor, you'll get quicker charging. And if we look at corresponding current time graphs, and remember they start at Vs over R, but I'll call that R1 because we're going to talk about the effect of changing the values of R. And the shape we had before, remember, going down, flattening out at the 0. If we get a smaller capacitor, right, with a smaller capacitance, then once again it will have less charge stored, so it will get there more quickly. The value it starts at though wouldn't be affected, it would start at Vs over R1. So smaller capacitance. If on the other hand we get a smaller resistor, then you're going to change this starting value. It would be Vs over R. Now if I've drawn that up near the top, so I'm actually going to use the logic for a larger resistor this time. That will give you a smaller starting current. So if this is Vs over R2, where R2 is greater than R1, then you'll start at a smaller value of current. But that means you're not pushing as much charge around the circuit. So in actual fact, it takes longer, and the curve will take longer to reach 0. So this is a larger resistance. But the original blue graph and the original, that red graph I've just drawn, just realised I've missed T off there, will both have the same area under graph, because that area under graph is the total charge stored. Now that applies to the blue and the red graph, because they were both the same capacitor, just a different resistor. And basically the larger resistor is just restricting the current, so everything takes longer, but you're still reaching the same total charge stored. So that would be the same area under graph. The green graph is a smaller capacitor, so it's going to have a smaller area under graph because there'll be smaller amount of charge stored. So we'll look at a worked example based on those ideas of charging. Some of these are just quite factual. Immediately after closing, so at T0, before anything has happened, at that point the capacitor won't be storing any charge. So Q will equal 0 coulombs. The potential difference there for across a capacitor will be 0 volts, so VC is 0 volts. Remember, the charge and voltage are proportional for a capacitor, which means all of the supply voltage at that point is across the resistor, VR is equal to Vs, and therefore we can calculate using V equals IR. So VR equals 10 volts, R equals 1 mega ohm, and we've been asked the current. Remember, anytime we're being asked current, if we're going to use Ohm's law, we've got to be using that with a resistor. You can't apply that to a capacitor. So V equals IR. And then you get I. 1 times 10 to the minus 5 amps. And then just for space, I'll answer B over here. The capacitor is fully charged. Then the voltage across the capacitor will equal Vs, equals 10 volts in this case. And the charge stored we can calculate using Q equals CV. Equals 2 times 10 to the minus 5 coulombs. Those are two calculations. If you had a question about, say, halfway through the charging, it would have to give you a bit of detail, like for instance, at a point the voltage across the capacitor is 4 volts. And then if you've been asked about the current at that point, or voltage across the resistor, you would need to use the fact that if that was 4 volts, then that would have to be 6 volts, because they would have to add up to 10. So you can work out that that's 6 volts and use that to get current and so on. So some uses of capacitance then. So timing circuits, values of R and C, resistance and capacitance, can be adapted to alter times for charging or discharging. So for instance, if you have a flashing light, then you can alter how quickly it charges. Smoothing, so the fact that the voltage changes slowly in time, particularly with larger resistances, can be used to smooth out sudden changes. And the other one worth mentioning is capacitive touch screens. And basically a good capacitor underneath a glass screen, and touching it with your finger alters the capacitance and therefore alters the voltage. And that change in voltage can be detected. And then lastly, traditional camera flash units. So using a small battery, for instance, which wouldn't supply a huge current to a bulb, you can let that battery charge up a capacitor. So a small battery can charge up a capacitor which can then discharge quickly to produce a large current. And that can give you a bright light.